The probability rule of complementary events. This presentation focuses on deriving and applying the probability rule of complementary events. What are complementary events? Complementary events are mutually exclusive and exhaustive. The word exhaustive means cover the sample space. That is to say, the fact that we are saying they are mutually exclusive, that means A intersection B is a set which is an empty set. And when we say exhaustive, we are saying A union B is equal to the sample space S. That means they cover the sample space. Now, deriving the probability rule of complementary events from cardinality of union of disjoint sets, because we are talking of mutually exclusive. So the sets themselves, they have to be disjoint when we are referring to mutually exclusive events. Assume that A intersection B is equals to an empty set, and A union B is equals to the sample space, right? That means by having the intersection being an empty set, the sets are disjoint, they are separate. Then, this is the situation we have. This is S, this is A, this is B. They don't have an intersection. If I add A and B, that will constitute the sample space. That is being exhaustive. That is this situation, right? Step number one, number of elements in A plus number of elements in B is the same as number of elements in A union B is the same as the number of elements in set S. True since A intersection B is an empty set and A union B is equals to the sample space. So as such, if I add this element plus this one is the same as A union B is the same as the number of elements in set S. I then divide both sides in step one by the number of elements in set S. This and this one divided by that, then this, which is the last part, divided by that. But you see that this is one and the same thing, save for the other ones. So as such, this fraction represents the probability of A, this one the probability of B, and this one is simply 1. So we are saying probability of A plus probability of B is equals to 1. That is probability rule of complementary events. Knowing as you do that complementary events are mutually exclusive and exhaustive. That means they don't have an intersection. Their union of those events coincide with the sample space. Once that happens, then we know the probability of A plus probability of B should give us 1. Right, let us summarize this probability rule of complementary events. In symbols, if A intersection B is an empty set and A union B is equals to S, then probability of A plus probability of B is equals to 1. That is what it means in symbol, and that is the best thing to know because it will be easy to remember. Then in words, if events A and B are mutually exclusive, disjoint, and cover the sample space exhaustive, then the sum of their individual probability is equals to 1. That is what it means. This is the sum of their individual probability. The answer I expect to get is 1. Okay, let us look at this example. Use the following Venn diagram if a number is randomly chosen out of the sample space, determine the probability of the events B complement occurring. B complement, that means what is not in B. Check B is this whole set. What is not in B is 9 is not in B, 12, 8, 4, 14, 16, 10, 16, 6, 15, and 1. They are not in B. So we want the probability that the number chosen is not in B, right? Then to do that, all what we need, we can actually separate the two sets, the set B and not in B, to come up with the two sets. How does that come about? Obviously, remember, when we count the probability or find probability of an event A, is number of elements in A over number in the universal set. This is just a reminder. Now, in our case, we are simply saying probability of B complement plus probability of B is equals to 1. What is not, remember, this is the B, right? And what is not in B is including these numbers and all this and all that. But if we are to add what is not in B and what is in B, we should have the sample space, right? So that is why we are saying it's equals to 1, because B complement and B are complementary events. Because this sign means because B complement intersection B is 0, because I've removed the B as a set, then I'm remaining with this portion and these other numbers. And in a diagram, okay, before I show you the diagram, then we are simply saying here now, the probability of B now would be, I take this, put it to the other side, it will be 1 minus probability of B, which is the same as 1 minus, then what is the number of elements in B? How many favorable? We have 1, 2, 3, 4, 5, 6. And we have this 6. What is the possible outcome? These numbers, they reach 1, 2, 3 up to 16. So they are 16. So it's 1 minus 6 over 16 is equals to 10 over 16. After you have simplified here, then it gives you 5 over 8. This in a diagram, this is the B. Check the B I've taken with the intersection, which is this one. Those are the elements that are in B: 1, 2, 3, 4, 5, 6. That is why you have a 6 in it. What is not in B? B complement, the red. Those that are in A, 10, 12, 6, 16, 14, 8, and 14. And those that are outside A, 9, 1, 15. This is what we have here. So this set, the whole in red, is B complement because it's not in B. So I now have two sets that are mutually exclusive, right? That means they are complementary. And again, if I add the elements in B prime and B, they give me the universal set or sample space, which is the S. So it is complying with the issue that events that are mutually exclusive and exhaustive, their probability is probability of B prime plus probability of B should give us 1, which is what is written here, right? So it's important that I had to separate so that you see the B standing on its own, then it's complement on its own, and there's no intersection whatsoever, right? So I then have to use that. But all the same, if you didn't use the idea of the sets being complementary, if we are to count the probability of B complement, if we count how many elements are in B prime, which is B complement, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It will be 10 over what is in the sample space, which is what 16. You still get the same answer. It's one way of checking. Does it work to say when events are complementary, they are mutually exclusive and they are exhaustive? And this is what I'm trying to demonstrate here. Then let us go on now to find Roman figure 2. A intersection B complement. That means we identify the A intersection B as a set, but we don't want what in that set. So the intersection is this one, right? What is not in that intersection? We have part of B, that is 3, 13, 5, 7, and 11, and 9. Then what is not in the intersection, we have also this part of what? Of A. Then the 15 and 1, right? So you can actually separate and have two sets, of which I'm not going to do that now, but now that you know, all what it means is I'll be saying the probability of the A intersection B plus probability of A intersection B complement. We add that and you should get 1, right? So we are saying the probability of the complement plus probability of the intersection should give us 1, because once we remove this intersection as a single set, what is remaining, what is not in the intersection, it's a complete set on its own, such that what is not in the intersection add to what is in the intersection, you end up with the sample space that shows that the two events are complementary and they are mutually exclusive and exhaustive. So we can actually write this, but I will show you something at the end whereby now you actually understand what is actually going on here. So as such, the fact that I want to find this probability, then this will move to that side and subtract to say, therefore, the probability of the complement of the intersection is equals to 1 minus the probability of the intersection, which is 1 minus probability of the intersection, simply favorable is 1 over 16, which gives us 15 over 16. Now, if you go to Roman figure 3, we want the probability of the complement of the union. That means the union would mean I'm adding what is in A and what is in B. Then I want what is not in the addition of the two sets, which will mean the elements 15, 1, and 9. Those are the only 3 elements that are not in the union of these two sets. So as such, what it means is probability of A union B complement plus the probability of the union, right? So as such, this is what it means, probability of the union complement plus probability of the union on this one is equals to 1. So what I wanted you to take note of, once you are talking of the complement, you write the complement itself, right, plus the probability of the inside, the union. As you can see in B, we did the same, probability of the complement plus probability of B. Here, we did the same, the fact that we want the intersection, so probability of the complement of the intersection plus probability of the intersection, which is what we still have here. When we are here, probability of the complement of the union plus probability of the union is equals to 1, what we have here. So that is a pattern that is followed by complementary events, when, especially in this case, when we are talking of the idea of being complementary, it's we are saying when we add the events that are mutually exclusive and exhaustive, we always have one. So in the last thing is we are counting on this, then we are saying this to that other side, then it subtract one, then we check what is in the union A, union B, you count all this, you find that they are 13. That is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So it's 13 over 16, which is 3 over 16. Right, this approach does not necessarily mean for us to answer this problem, I had to use the idea of always coming up with one. No, I'm giving this example so that you know that the approach of complementary events makes life easier in some instance. And besides, you need also to understand that because you might be given situations where you are not able to count, but you're supposed to apply the idea of events being complementary. Okay, I think with that, that is the exact thing I just wanted you to know when it comes to what are complementary events. What is key to remember is complementary events are mutually exclusive. That means they are disjoint events and they are exhaustive. That means the sample space coincides with the events that are mutually exclusive.